All right, let's get started. So I'm recovering from a cold over the weekend, so I might have a bit of a cough, but should be fine other than that. Today we'll talk about more process control, more exceptional control flow, things that don't usually happen in programs, or at least you don't expect when you write a program. It doesn't look like it's going to do anything like that. And then if we get to it, perhaps we'll talk a little bit about starting and stopping processes, that sort of thing. Okay, but first, any questions on the homework?
How do we get the answer?
You said it's not worth it to go through and try to call something in main that's in the so.
Yeah, so if you want to call other functions from inside main.
Like, I call server and then server calls real server.
Mm-hmm. That's it?
Is that how it works?
I don't think that's how it works, but
Okay, then never mind.
In general, any call from main to lib.so is going to need the dynamic linking process, right? Which means it's going to be a real pain. Like, you have to now grow your global offset table and your procedure lookup table, and then rewrite the. It's going to be a huge mess. So what you can do is maybe repurpose one of the existing entries if you'd like. Maybe some of you have noticed that that's sort of what is done already in main.c. So you don't necessarily have to do that.
I know you mentioned netcat.
Mm-hmm.
That was a CS450 type stuff. Would it be worth it to check it out, or is it way above?
Netcat is awesome and super easy to use.
Did you just use the Wireshark equivalent?
Let's try it. Let's see, CS. Netcat is, I don't know if you've used cat. Right? You have a file. We have a file, routes.json. Okay, there's a file. And I could also say just cat, and then it waits for input, and it outputs whatever I input. So I can say cat routes.json, cat again, and then cat is just like output whatever. With netcat, it's the same thing, output whatever, or input, goes both ways, but it's from the net instead. So now I tell it I want to talk to the server at that port, and maybe I have to send it something. I think I have to send it something. So I say echo hello, right? Oh, it's called netcat on some systems, NC on other systems. Oh, and there's the output. So that's what I got. That's what I got from the server. And if I want, I could then use hex dump on that. And there's the code. I cannot use object dump disassemble because this is not an ELF object. This is just a little bit of, a few hex numbers, right, that go in somewhere. They have to sort of fit within the right context to really be assembly. But maybe you recognize this one, for example, here. This looks very much like a jump to a negative address, like to a negative offset. So that's something what's going on in there. And then most of it is just garbage like this, right? No ops. Very good. All right. Okay. So, yeah, that's that. Any other questions on the homework? Who's finished? All right. Awesome. Okay. It's not even Tuesday yet. So the next homework, I won't talk about it in detail today, but the next homework is making a command line interpreter. So basically whatever we have here, right, we want to be able to run a program that then looks just like this. And then we're typing commands in, and it runs those commands, and it supports pipes, and it does, pipes being this this thing, right? Yeah, okay. Anyway, we'll talk more about that later. The hard problems are probably the piping and the input-output redirection between lots of different processes, sort of thing. So that fits in well with the current chapter, which is chapter 8, exceptional control flow, and we'll go through pretty much all of the. I think we'll cover all of chapter 8. So we're done with chapter 7 now, and chapter 9 we've already covered the parts that we're going to cover. Excuse me. Okay. Getting back to where we were.
I didn't see the video start.
Oh yeah, it did start. Yeah. Thank you.
Are those notes up on like
lecture note or something? Or
They are hiding away in the pub folder on bits. I update them every now and then, but I'll make sure to update them this afternoon so you can get them. I think I saved them both in this Omni format and in RTF, which can be opened with any text editor. Okay, so last time we talked a bit about system calls, right? So the way a system call works is you make an interrupt happen. An interrupt, or I think they call it a trap when it's a software-based interrupt. So that then creates a jump, makes the processor jump immediately to a well-known address in the OS that then processes, tries to figure out what happened. Right? Why did the user create this, make this interrupt happen, and then do something for that user? So there's a giant security benefit to this. You can imagine, let's see if I can make a example. Yeah, okay. So example system call, okay, whatever. First, we might have a little bit of code that checks, that's too small. Check process credentials, and then we say do dangerous thing and return. Right? So we only are allowed to do this dangerous thing if the process has the credentials to do it. Right? So perhaps the process is running as the administrator, or was run by the administrator, in which case they're allowed to say reformat the root disk. Otherwise, they should just be denied. Of course, reformat is not actually a system call. That's a user-space program, but writing directly to the to the disk rather than going through the file system, that would be something that you'd require administrative privileges for, and also that sort of fits in the system call concept. Okay. So anyway, a system call can only start from the very beginning, right? You have a pointer that goes to here because your interrupts, the interrupt jumps always to the same address, and this is defined in this little interrupt vector. Imagine if instead the user program could just jump to, let's call this 1, 2, addresses 1, 2, 3, right? So the interrupt vector always points at address 1. So we're always going to check the credentials, and if it doesn't work, maybe return error, right? Okay, so alternatively, you could say, okay, why don't we just jump to this address? Rather than going to this whole system call business, right? You just say call, and you have the address of it. The addresses are not known, but say we could figure it out. And that seems like a nice solution, and you don't have to have the interrupt. There's a lot of extra handling, a lot of extra trouble handling system calls. So what would be the problem here if we were to allow that sort of thing? Well, so we tell you have to call to 1.
Oh, you're saying jump straight to. Okay.
Any process that gets code executed, basically, the operating system can do anything. There's no credential check.
Well, there is credential checking. We tell them you have to jump to 1.
I thought you said there was no credential check.
Ah, but there is credential checking. It's right here. Well, the thing is, it's not enough to tell them they have to jump to 1. If they don't want to, they can just, it's a call. In your own process, you can call wherever you want. So they can just call to down here right away. And then all bets are off, right? Now there's no credentials checking. And bad things will happen. Of course, that would only also happen if the process suddenly got these super user privileges. Right? A regular process cannot write to a device. A user process cannot write to a device. So there's two parts that have to happen. First, you have to be able to jump anywhere you want, and then you have to be able to execute that code as super user. Neither of those are true, of course, in a regular operating system. We have a bit saying you can only execute this, or in fact, you can even only read this code if you are a super user. And how do we become a super user? You're a user process, now you want super user privileges. Only through interrupts, actually, yeah. interrupts, traps, something like that. And the only way then to become a super user is to go through one of these entry points, which always have some sort of credentials check. So, well, that's not strictly true. If you're not going to do anything dangerous, if you're just trying to read your process ID, there's not going to be any check. It all depends what you're doing. Okay, so that's one kind of exceptional control flow. Right? I'm creating this exception, so that's pretty predictable in a sense, right? I'm making it happen, so therefore I should be able to expect what's going to happen next. What about something like this? So I run. Let's see, what can we do here? I'll just run cat. Right. So actually, cat is kind of a boring program. Do we have a more fun program? Homework 2. What was that? Okay, homework 3 then. Whoa. I guess I don't. Oh, bits. Which one was homework 2? Oh yeah, so it's gonna run kind of slow. Okay, good. Okay, so this program, it doesn't. Oh, it's not running slow enough. Was there a basic as well? Okay, cool. Okay, so it's this program is not expecting any input. Right? It's not listening for any input, and yet if I hit Control C, it got a Control C and it stopped running. What happened there? Any ideas?
Is the OS always listening for something for another input?
The OS is in fact always listening for all sorts of input. The only way that a process can get input is from the OS giving it. Right? As always, the process cannot talk to the keyboard or anything else. It can only ask the OS, please give me some input from the keyboard, and then we'll see. But the process in this case did not ask for some input. So this is called a signal. Let's see, what do we have so far? This was just system calls. Okay. Types of exceptional control flow. So we have system calls. Let's think about signals for a bit. So signals are a sort of strange out-of-band way for the OS to tell a process things. It's not just the OS. I can actually send it the same signal. Let's do that. Like this. The program is ominously named, right? It's kill, but you don't just kill. With this, it's a. I can't think of a good analogy. Maybe a knife. You can do useful things with it. Okay, so let's try this again. So I'll run homework. I'll run this basic. Now with PS, I can find. Oh, there's the process, right? And now I want to. I can kill it from here, just right away. And now that killed it good. Now it was. That's it. Let's try it again. So I don't have to look through this thing. I'll say grep basic. Okay, so there's the ID again. I'll say kill minus up. See? Now it got a hang up signal. Okay. That was actually the process outputting this. So this is not the OS coming in saying, oh, you should write out hang up on the command line. That's not what's going on here. The process received a signal from another process. OS was only involved in the sense that it delivered the signal. Right? It was told by this process to deliver something, and it did. Now, if I'm running it here and I hit Control C, the same thing happens, but now it's the keyboard driver or something that delivers a signal. Actually, it's probably. I have to look this up. I'm not sure who decides that the Control C should deliver a signal. Probably the terminal driver somehow, but I'll have to figure this out. Okay, so a signal gets delivered to this application, but most of these signals are maskable. Maskable and non-maskable. So with a non-maskable signal, there isn't anything you can do. You may have seen this trick before. So here, let's do this one more time. Oh, 8-0, yeah. So that said killed. Huh. I don't know why that said killed. Anyway, I would have hoped that it didn't say anything. So there must be a handler that's in there by default. Anyway, -9 is one of many signals. So there's signals between 0 and what? It doesn't say in here. Maybe it says in kill. Oh, here we go. Okay, so there's all sorts of signals. And I guess they don't all have numbers in here, but here, kill is the only signal that can't be blocked as far as I know. So if you have a process that just won't die, you keep sending it signals, but it just won't die, you can always send it a -9, and then it will die, unless your operating system is broken. Let's try one more thing here. So here with nano, I'll send my nano a signal. Okay, so that seems to have killed it. What if I call it something else? Give it something else. Sig int, I think, is nice. That didn't do anything. So Control C, that's the sig int. If I hit Control C here, now I'm hitting Control C. It says which line I'm on. So this means we can do whatever we want with most of these signals, except for this the number 9, which is you gotta die. So let's see if we can get that to work for us. Okay, who's used sleep before? You can pause for as long as you want, but you give it a number, that's a number of seconds, that's just wait for a little bit. And that's actually, it's more interesting than it seems. Because when it's sleeping, the process is not actually in the CPU at all. It's not like it's looping, and no, it's just sitting away in a corner somewhere in memory, and the OS remembers a second later it should wake it back up. We'll see how that works in a little bit. But for now, let's just have this sleep here.
Is that a system call?
Sleep is a system call, yes. Otherwise it wouldn't be able to do that kind of magic. Okay, let's see. So I want to try catching a signal. So we'll just go like that. All right, so now I have a little function. I want this function to be called whenever a certain signal comes in. Do it this way. Say for signal, sig int, interrupted. So I think that should do it. This actually means the same thing as that. All right, if you just specify, this is the address of the function interrupted. Same thing as if you specify the name, just give the name of an array. It's really a pointer to the beginning of the array. Here it's a pointer to the beginning of the function. Let's try this out. Oh, but it's probably going to be upset because I need to include some stuff. Perhaps like this. All right. I want to just check that. Signal.h. Yeah, very good. Oh, here you see. Okay, so it says you're supposed to pass in a sig handler T. Handler. Okay, so what's a sig handler T? It's this. And so this is function pointer syntax. I don't know if you've used any function pointers before. They are a little hairy, especially the syntax, because see, this is the name of the type, and then like what the type looks like is all it's on both sides of the name, which is really weird, I find. But anyway, so a sig handler T is a function pointer that returns void and takes an int. So we should probably give it an int. That might be the signal type. Let's just print it and see what comes out. Okay, let's try this. All right, we're waiting. Hit Control C. Okay, so there we are. Sig int. I wonder if that's number 2. Let's try that out. So when I hit Control C, we apparently got a sig int, and that's number 2. All right, good. So I can't get out of here. So what do I do then?
Kill it with -9.
Exactly, I can kill it with -9. There's another little neat trick. I can hit Control Z.
It's background.
No, it's not backgrounded yet. Now it's just sitting there. If I type jobs, it's sitting there. It's not running at the moment, but I can say FG and then it continues running. Okay, that's not very helpful. I can say BG, and now it's actually running in the background for this shell. That's sometimes not so helpful either. Let's see. So maybe I can tell it to go FG. FG1. Oh, yeah. This is not. Oh. Oh, okay. You're right. It actually worked. The FG1. I just didn't realize. All right. So let's do this one more time. So now it's running in the background. See how my command line is still there? It keeps coming back, right? But then when I do the FG %1, which means job number 1, now the command line isn't there anymore. So now it's actually in the foreground, which means I can send a signal to it by hitting Control C. I wasn't able to before. So now if it hit Control Z again, it stopped. Okay, but I actually want to get rid of it. So let's just kill %1. Okay, so that terminated it. So that actually sent a sig term to it. So if we want, we could take it a little further.
You can't catch a 9 on this, right?
You cannot catch a 9, exactly.
The only one you
You can catch everything else. So let's just try that too. And then sig stop is the Control Z. So we'll just do all of those. So now we have an invincible process here. Control C, Control Z. Oh, hey, what happened? What's the other one? Oh yeah, we wanted to kill it. So let's. Oh, what happens if we send a signal to an already stopped process? Let's try it. Oh, we woke it up. Okay. So that was number 15. Right, so that worked. Stop apparently did not work. Maybe I have had this wrong somehow. Let's see.
How did you send 15 again?
Oh, I told it kill %1. So %1 is replaced by the process ID. It's just the job number 1 in that jobs list. That's really only a facility of the command line shell. Those %1s don't exist in the OS in general. But I can also go from here if I want. Hey, wasn't it called signal?
Yeah.
Oh no, it's called a.out because I didn't make a binary called signal. It's only the source that's called signal. Anyway, there it is. So now I can send a kill sig. What was it? Sig kill actually was the one we wanted to do. Yeah, so that one got caught.
Try sig
Oh,
stop.
oh, I have to do it's minus like this. Oh. What? Oh, I see. Yeah. Okay. So it got. Was it? Which one was it that? I thought 15 was one we caught. Or was? Now I'm all confused. Let's see.
15 was term.
Oh, 15 is the one. No, that's term. Yeah. Oh, and I'm not catching term. All right. So there's lots of these signals that seem to mean almost the same thing. Hang up, kill, terminate. What else? Oh, and then there's stop. For some reason. Oh, stop cannot be blocked. There we are. Okay, so there's two of them that can't be blocked.
Stop and Control Z.
Stop is Control Z, yeah. Well, in this terminal, but yeah, in almost all terminals. Oh, look, there's more. So you've seen probably this one before, right? Sig seg v, so seg fault. So that happens not from that's sent not from anyone typing it in. In fact, maybe you can. Should we try it?
Yes, we
Seg v. Okay, so here we see that there's nothing special about these. Like all the signals are just signals. So we could probably then put in an exception handler for segmentation fault. All right, let's see what happens.
will be using this for our debugger.
We actually won't be using that for the debugger, but yeah, that's a possibility. Okay, let's try to put a seg v in here too. See what happens. Well, I don't think it's going to screw much up right now because we don't actually have a segmentation fault.
Yeah,
I mean,
if there was a
If there was a seg fault, yeah, let's make that happen after. Let's try, first see what happens here. Okay. Okay, that was at number 11, so that's no big deal. Wait, 11, was that seg v?
I don't believe that number.
Maybe it was. Yeah, okay, good.
How come it didn't seg fault? Oh, yeah.
I got it. So now let's try to actually seg fault our program and see what happens. Do something really bad. Yeah, so am I able to get? No. And now it's in the background. Okay, now it's in the foreground. Ah, okay, now kill -9, and we should be good. All right. But type jobs, there shouldn't be anything left. Okay. Let's give that one more shot then. So what can we do to seg fault this thing? I guess we can do. What's that? Huh? Dereference no, that's a different seg v, isn't it? Oh, maybe it's not. If you dereference a null pointer, do you get a seg v? Yeah. Oh yeah, so it's not the same as division by 0. That also gives you a different. There's a special signal for division by 0, but yeah, let's not go there. Okay, so try that. It's a strange thing to write. Uh-huh. Oh, wait. Oh, there's an error. Yeah, okay. So let's dereference a void pointer then. Okay. Huh?
Wait, so we can actually print stuff from protected addresses?
Oh, I didn't. I don't know what's happening at the moment.
Shouldn't be printing A. I called it. Oh no, we didn't.
I thought we caught it. So I think it's just I think it's just not running that for some reason. So let's just see, because this sort of thing is always best to check the code. Since you're a computer scientist here, you actually know what is going on under the cover. So let's just do that. See if GCC actually did what we thought it would do. Because it's easy to speculate, but sometimes it's better to just know. Okay, where's our main? There. Okay, so those are all signal stuff. Okay, so where's our? There's our loop, right? Main plus. So it's jumping to. That's another signal. Here we're printing. Yeah, look at that. It doesn't actually output any code for this.
Probably because we never used the value.
Probably, yeah. I figured this is pointless. Why should I work for you when you don't give me anything reasonable to work on? Okay, let's see if we just printf that value instead. Oh. Ah, come on. There. Okay. So now it has no choice. Error, invalid use of void expression. Okay, fine. We will pretend it is an int. What am I doing? Yeah, not even a warning. That's nice. Yeah, good stuff. Yeah. So there we are. Got very upset.
So it doesn't actually print what's there though. It's just like, yeah, it's custom.
Yeah, there actually isn't anything there. That's a sort of a. Yeah, that doesn't work either. We've made an armor-clad process here, but that should do it. Okay. Okay, so there. I think there's something we can do here. In this case, it's difficult because there's never going to be anything at 0. In general, though, say we got a seg fault for some part of memory, we can catch that, and then we can tell the OS to put something there. Right? We can use mmap to put something at that address, and then actually for a signal like this seg-v signal, it returns and tries the instruction again.
So we could, for instance, have a program return null whenever you get to a segment instead.
Yes, or you can mmap a file in there and just read whatever's in the file. There's no limits to the things you can do.
So we would basically be corrupting our parts of memory that we wouldn't
No,
normally have access to.
you're not corrupting anything. So maybe we should try this. We have time. I've never done this, but
How would you do it if you have a program that you have multiple places where you might get a seg fault with different behavior depending on where the seg fault is?
yes, I believe you can also get the address which created the problem. I don't know where that resides, but you can see, oh, this instruction made a boo-boo. You know, what do you want to do about it? Okay, let's see. So we want to dereference, and we want to put something. Oh, I don't know. What's a reasonable address? Let's see.
OX68.
Yeah, but how are we gonna get exactly right here with you guys? Oh yeah. Well, that's fine actually. Let's just look at that one. Pmap. So pmap tells you what it all looks like. Okay, and that looks reasonable. So I want to go somewhere after this. Somewhere. Yeah, I don't have a heap. So I go 900. Or put a 9 there maybe. See what happens. They just didn't get a name. I'm not sure what they're doing there. Let's figure this out first. Okay. So we're going to dereference an address that we're not allowed to dereference. See, so what's a... Actually, we can just put a 5. Go right after there. Make sure we're not creating any big trouble anywhere. Okay, so I'll put that... Actually, it may not... I'm a little concerned that at some point we'll need a heap. Like maybe... I don't know who would need a heap here, but I don't know. So I want to make sure I end up over the heap. So we'll just put a 9 there. Okay. So there's our address. And now we want to put printf. No, not printf. Now we want mmap. Okay. So here we can tell mmap where we want it, right? So I want it at that address. I want it to be. You actually can only make it in the 4 kilobyte increments. And we want some protection. How does it go? That's the protection. Prot read. And then flags, file descriptor. We don't have a file descriptor. And an offset. Okay, so file this. I think we have to tell it here. Then. Map private. Okay, we'll go map private. It needs to be anonymous. Map anon. Oh, there we go. So an anonymous mapping means it doesn't have a file behind it. So we're not saying, oh, map this file in. We're just saying, give me some memory in this area. Map anon. Okay. Oh, wait. Okay. Anonymous, I suppose we should have done. And that should be it. Okay. So I believe I don't even have to pass in the rest of the parameters. All right. In what happens in C, it's just putting these parameters on the stack and then jumping to the right address. That address, well, they're gonna look at those parameters if they need them. If they don't need them, whatever. So it's not so. I don't think it's that important what we write here. Okay, let's try this. Actually, let's make sure we got everything right here. So what should happen now is,
You may not want to have that off.
let's try without it first. And then we should get all these hays. And then with it, it ought to work the first time around, but we should get a hay in there anyway. Octal constant. So that's a bad address there. We want to say 0x. Right. If you don't specify 0x or a b after, then it's an octal for some reason. I don't know who uses octal, but what? Oh, yeah. Okay, so that's still not working.
What are we mapping to?
Okay, I got lazy here. It didn't work. Kill all is a handy little program. It goes by the name instead. Of course, it's going to kill everyone that's called a.out, which may not be such a good idea. So it depends what you want. What are we mapping? You're saying?
Yeah.
Nothing.
So 0 or
Yeah.
nothing?
So when you do an mmap, you can either say, oh, put this file in memory, or you can say, just give me some memory. So this is what malloc does, right? If you get a very large allocation, malloc will just mmap a large chunk, and that's it. So that's what we're going to do here, just to fill it in. What's that?
Every loop run does it.
Yeah, but are we going to get back in there? I don't think so. Because now it's going to be a valid address. You won't get a 6xv, and we're good. Of course, if I hit Control-C, then it's going to get weird. Because then I send another signal, it's going to run that anyway. Yeah.
So it's just setting up a page file, it's not clearing the memory out, just giving you an address saying, use this space.
Yeah.
And whatever jumps in there.
No, actually, it has to clear it. For security reasons, the OS has to clear any memory it gives you. Because someone else might have written secrets to there. before. And it's not so unlikely. Okay, now we want to change this. Wow.
Interchange your address.
Sysmman.
Man.
Yeah, it's mman for memory management, I think. Oh yeah, I'm gonna get a 0x there. Thank you, whoever said that. Oh, I got an error. Okay, fine. You know, sometimes you don't get errors, and sometimes you do, and I'm not sure. Maybe it's because it's the declared function. That's probably it.
It may also be a distribution.
A distribution.
It's like
maybe.
differently defined depending on the use case.
Yeah, could be. Okay, look at that. It just works. And what's in there? A 0. Yeah. So that's 0 because it was cleared out. But of course, 0 is going to be the most common value in memory anyway, so maybe we just got lucky. Probably not.
Can we get that memory without zeroing out first?
No. Well,
I'm trying to think.
Retro system.
if you're a super user, you can probably find a way. But to a user space program, there's no. It's not an option.
Can we request malloc to give us like specific piece of memory, or
That's what we just got. Oh, specific piece in our virtual address space, yeah. In physical, no. So we can say this part of address space should fill up with memory, but which pages it uses, that's even going to change as we run, right? If there's a lot of memory pressure. So there's no real control there. And now what happens if I... Yeah, so now we're actually mallocing the same place. We're trying to mmap the same place over and over. I'm getting error codes back, but it's not so bad. I mean, it's saying, oh, no, I can't do that because it's already taken, but I'm not handling the errors, so nothing's happening. Okay. All right. So, long story short, signals are just one more way that we can get some input to a program. You can use that to run your program too, if you want. Right? You can have this little control C means something in the context of your program. Like in Nano, it means figure out what line I'm at. But a difficulty with this is that they happen anytime, right? So we don't. You could be running some other part of your program, and suddenly your signal function comes in and runs instead, and that can screw things up. So this is our first encounter with real concurrency, at least in this. You haven't done any threads before, have you? No. So this is the first kind of concurrency that we encounter, and it's actually something that's been around for the longest as well. Same thing with interrupts. You're doing something, you're halfway through your big fancy addition, and then someone else comes in, uses the same variables, puts some other values in there, and disappears. And now you're stuck with some garbage in your registers, and you don't know what's going on.
So the only non-muscular signal is -9?
No, there was a stop as well, which was 15, I think.
No, that's
Oh, that was terminate, yeah. Don't know which one stop is.
and after I receive the signal, let's say I receive the signal and I want to call some function. That's why I do it. And then after it's done, do I come back to where I was before?
Yes, exactly. So that's what happened in our code here, right? First we set up these signal handlers. That's not actually making any signals. It's just saying, oh, if I get that signal, call interrupt. And then in the loop, the signal happened when this was done the first time, because we did something illegal. It jumps to here. It changes the memory layout. And now it's actually going to rerun. For seg v, it's going to rerun the same line again.
Oh, still.
And that time it's actually legal. So now we got the value 0, because that's what was in that little piece of memory. Yeah. So signals are the closest we get to interrupts in a regular program, but they sort of behave the same way.
You said that when it fetches a signal, it handles that and then continues running. But when I saw it running, I noticed that the sleep one didn't really get evaluated. It seemed to run much faster than the sleep one.
You wouldn't get there too.
Oh, yes, that's probably that's a good point. Yes, so signals do make some things behave strangely, and I think sleep would be one of them. So you can interrupt a sleep. So let's try that too. We have a long sleep, nice nap. Okay, and now and it's continuing, right? So I'm interrupting their sleep, but yeah, it's not pleased, you know, but it goes back to sleep. Okay, so this sort of brings us to full-blown concurrency now that we have multiple programs running or multiple processes at the same time on a single CPU. You can actually implement this with signals. You don't have to have the OS support threading. You can do this yourself as an application library, and I think we'll do that as one of the last couple of homeworks. That's called green threads, if you've ever seen that in Java, perhaps. Anyway, so there the idea is you make sure you get a signal every now and then you change everything around, do a little bit of assembly, right? Change all the stack pointers around, do everything, fix everything up, and then jump back to the other thread. So you have two different threads of operation, and you can sort of decide based on these signals what to run when. Actually, we go until 50, right? Yeah, so I think we're out of time here. Next time we'll talk about the homework, and then we'll also get onto fork, making multiple processes and how that all works. We may make a fork bomb tomorrow. No, on Wednesday, yeah.